In this segment of our series, we'll take a closer look at the components in a control system and explain how they help keep a system operating effectively and efficiently to maintain the desired temperature. The contactor is one of the components in a control system that's used to control the operation of an electric load. Contactors cause sets of electrical contacts to open or close automatically to either energize or de-energize system loads in response to the load requirements. The two main components of the contactor are the coil and the contacts. The contactor coil generates a magnetic field which pulls the contacts closed, energizing the system load that's being controlled. Contacts on the contactor are connected to an armature that helps ensure that all sets of contacts open and close at the same time. Contacts are rated by their current carrying capability. Large loads require contactors with a high current rating. In this schematic diagram of a small residential air conditioning system, the two sets of contactor contacts are used to energize both a compressor and a condenser fan motor. In larger systems, each compressor or fan motor may very well be controlled by its own contactor. When a contactor fails to operate properly, there are three areas that need to be checked: the coil, the contacts, and the mechanical linkage. The failure of any of these parts will cause the contactor to malfunction. The coil of the contactor can be easily checked with an ohm meter. If the resistance of the coil is infinity, the coil is said to be open and must be replaced. Infinite coil resistance indicates that there is a break somewhere in the coil. Some coils, such as those on a potential relay, have very high resistances, so the proper resistance scale should be used. If the resistance reading through the coil is 0 ohms, the coil is shorted and must be replaced. If there is a measurable resistance in the coil of the contactor, chances are that the coil is good. The contactor contacts should be smooth. A visual inspection can be done to check the condition of the contacts. Here we see both good and bad contacts. Contacts can also be checked with either a voltmeter or an ohm meter. When checking the contacts with the voltmeter, the test leads of the meter should be placed across the contacts as shown here. The coil of the contactor should be energized and the contacts should be in the closed position. A voltage reading across the contacts that exceeds 5% of the supply voltage indicates that the contacts are pitted or bad and need to be replaced. If an ohm meter is used to check the contacts, there should be no current flowing through the contacts, but the coil should be energized. The wires should also be disconnected from the contactor contacts. When the contacts are in the closed position, the resistance reading through the set of contacts should be very close to 0 ohms. Always be sure to check all sets of contacts. A high resistance reading indicates that the contacts are no good. The mechanical linkage of the contactor can be checked by simply moving the armature of the de-energized contactor. The linkage should move freely. Similar to contactors, relays have a coil and sets of electrical contacts that are used to control the operation of system loads. The main differences between relays and contactors are that relays are typically single-pole devices and have lower amperage ratings than contactors. Normally open contacts are drawn as two small parallel lines. Normally closed contacts are drawn as two small parallel lines with a diagonal line connecting them. On smaller central air conditioning systems, the indoor fan is often controlled by a relay, since the motor typically has a low current draw. The indoor fan relay coil is labeled IFR in the diagram. When the thermostat calls for indoor fan motor operation, the low voltage fan control circuit is energized, causing the IFR contacts to close. Relays can also be used to change the speed of a fan motor depending upon the system's mode of operation. In the schematic shown here, the indoor fan will operate at low speed during the heating mode and at high speed when operating in either the cooling or fan-only modes. Just as with the contactor, checking the coil of a relay involves taking a resistance reading of the coil. Checking the contacts of a relay is also done with an ohm meter. The resistance reading should be 0 ohms through a set of normally closed contacts. A voltmeter can also be used to check the contacts of a relay that is in an energized circuit. When the relay coil is energized, the voltage reading should be 0 across a set of normally open contacts, as these contacts should now be in the closed position. Relays are typically throwaway devices, so if the relay malfunctions, it's best to replace the entire device. Fuses are the simplest of overload devices, constructed of an internal element that will melt if excessive current flows through the circuit it's protecting. Fuses are often used to protect resistive loads which have no coils, such as heaters. Here we see that each of the 3 heaters have 2 fuses protecting them. Once the fuse blows, it must be replaced. Overload devices that are used to protect inductive loads, such as motors, are somewhat more complex because the current draw of inductive loads is not always constant. When a motor is initially energized, it draws substantially more current than when the motor is up and running to speed. For example, this motor draws close to 70 amperes when it's first energized. This is the motor's locked rotor amperage. As the motor reaches its design speed, the current draw drops down to its full load amperage. An overload commonly used to protect small motors is the line break overload, which breaks the power line that supplies power to the device. The most common type of line break overload has a bimetal disc that flexes with changes in temperature that result from excessive current flow through the circuit. When the current exceeds the acceptable level, the heat generated will cause a bimetal disc to warp, causing the circuit to open. This will de-energize the circuit. Some line break bimetal overloads are also equipped with devices that sense the surface temperature of the controlled device to provide a more accurate range of circuit protection. The overload is wired in series with the common terminal of the motor as shown in this schematic. The other type of commonly used overload is the pilot duty overload. Unlike the line break overload, the pilot duty overload breaks the control circuit, not the power circuit of the device being controlled. Notice that the overload contacts are located in series with the contactor coil, not the compressor itself. 3 common types of pilot duty overload are the current type, the magnetic overload, and the electronic overload. Troubleshooting overload devices is relatively easy since they only have one set of electrical contacts. To do this, an ohm meter is used. With the power disconnected, an overload in the closed position will have a resistance reading of 0 ohms. An overload in the open position will have a resistance reading of infinity. Internal overloads are harder to test. A reading of infinity through a motor winding may mean that the overload is open, or it may be an indication that a motor winding is damaged. For this reason, the compressor should be cool, giving the overload time to reset itself. If the resistance reading is still infinity after the compressor is completely cooled, chances are that the internal overload has failed. Transformers are electrical devices that provide the low voltage power source for control circuits. The transformer is supplied with line voltage and transforms it into the desired voltage. The transformer is made up of 2 windings, the primary and the secondary. The primary winding is where the power is supplied to the transformer. The secondary winding is the power source for the control circuit. There is no physical connection between the two windings. The voltage is generated in the secondary winding by induction. If the primary windings has more turns than the secondary, the voltage at the secondary will be lower than the voltage supplied to the primary winding. This transformer is called a step-down transformer. If the primary winding has fewer turns than the secondary, the voltage at the secondary will be higher than the voltage supplied to the primary winding. This transformer is called a step-up transformer. Troubleshooting the transformer is easily accomplished with the help of a voltmeter. First, the technician should check to make certain that the voltage is being supplied to the primary winding of the transformer. If there was voltage at the primary, but not at the secondary, the transformer is defective. If there's no voltage at the primary winding, there's a problem with the circuit that supplies power to the transformer. The thermostat responds to changes in temperature by opening or closing sets of electrical contacts in an effort to maintain the desired temperature. A heating thermostat closes its contacts on a drop in temperature. The schematic of the heating thermostat is shown here. A cooling thermostat closes its contacts on a rise in temperature. The schematic of a cooling thermostat is shown here. When the system is set to the cooling position, current flows through the system switch to the cooling thermostat, which operates the cooling portion of the system. If the system is set to operate in the heating mode, current flows through the system switch to the heating thermostat, which operates the heating portion. Thermostats are typically manufactured with either a bimetal element or a remote bulb. The bimetal thermostat is made up of two dissimilar metals that are bonded together. They expand and contract at different rates, causing the bimetal disc or strip to flex. This flexing causes electrical contacts to either open or close. The remote bulb thermostat utilizes a sealed bulb that's filled with a mixture of liquid and vapor. As the temperature of the bulb increases, the pressure inside the bulb will increase as well. This pressure is used to push a diaphragm, which in turn causes electrical contacts to open or close. Thermostats can be designed as either line voltage or low voltage devices. Line voltage thermostats are designed to make and break line voltage circuits and can be found on such systems as window air conditioners or electric baseboard heating. Low voltage thermostats are commonly found on residential central air conditioning systems, as well as on most commercial and industrial systems. Low voltage thermostats are desired because they are typically less expensive than line voltage thermostats and are safer, since the voltage in the device is lower than in the line voltage version. When checking a thermostat, it's important to remember that the thermostat is a set of switches that controls the operation of the other system components. Each manufacturer uses a different labeling legend, so be sure to have the service booklet available. Many thermostats operate with mercury-filled bulbs that are connected to bimetal strips. These thermostats must be mounted perfectly level to ensure proper operation of the system. A voltmeter is probably the most useful piece of test equipment when troubleshooting thermostats. Voltage readings are often taken at the sub-base, which is where the control connections are made for the thermostat. If the contacts on the thermostat are in the open position, there will be a voltage reading between the two terminals. If the contacts are in the closed position, there will be a voltage reading of 0 volts. Some thermostats control only heating equipment, some only cooling equipment, and some control both. One type of switch that's commonly found on air conditioning and refrigeration systems is the pressure switch, which opens and closes its contacts based on the pressure it senses. The high pressure switch is connected to the discharge side of a refrigeration system and opens its contacts if the pressure reaches a higher level than the predetermined set point. Most high-pressure switches need to be manually reset once they open their contacts. This helps ensure that the system will not operate under unsafe conditions. The low-pressure switch is connected to the suction side of a refrigeration system and opens its contacts when the pressure in the system falls below the predetermined set point. Low-pressure controls are often used to disable a refrigeration system if it should lose its refrigerant charge. Just as with any other switch, the voltmeter is a valuable piece of test equipment to have when checking pressure switches. High-pressure switches should always have a reading of 0 volts across the device unless the system has reached unsafe pressure levels. With the system operating, there should be a reading of 0 volts across the low-pressure control, indicating that the switch is in the closed position. When the contact on the pressure control is open, there should be a voltage reading across the contacts on the device. Humidistats are designed to open and close their contacts based on the level of humidity that is present in the occupied space. If the humidity is lower than the desired level, the contacts on the humidistat will close to energize the humidifier. When the humidity reaches the desired level, the switch will open, de-energizing the humidifier. Oil safety switches operate in a similar manner to the low pressure switch. If the oil pressure in a system falls below the acceptable level, the device will open, de-energizing the system. In order to read the oil pressure in the system accurately, the switch is connected to both the oil pressure port on the compressor and the compressor crankcase. The oil pressure of the system is the difference between the two pressures. Contactors cause sets of electrical contacts to open or close automatically to either energize or de-energize system loads in response to the load requirements. The contactor coil can be open, shorted, or good. Similar to contactors, relays are also used to automatically control the operation of system loads and are tested in a manner similar to that used to check contactors. Overloads protect system loads from an overcurrent or overheating condition by opening the circuit that feeds power to them. Troubleshooting overloads can be done quite easily with an ohmmeter, since these devices typically have only 2 wires. Transformers provide the low voltage power source for many control circuits. They can be field tested by taking voltage readings at both the primary and secondary windings. Thermostats open and close their contacts depending on the temperature they sense. Thermostats can be remote bulb or bimetal devices. Thermostats can be checked with a voltmeter. The voltage across an open set of contacts should be the same as the circuit voltage. Pressure switches open and close their contacts depending on the system pressures they sense. Humidistats are designed to maintain the desired level of humidity within an occupied space. Oil safety switches ensure that refrigeration systems operate with ample oil pressure. This series continues in the next segment on heating control devices.